what we saw in the previous hour is that if we have a metric, we can learn, we can define fair learning. I told you, and we didn't go into it, but we can also use convex optimization techniques to actually efficiently learn fair classifiers. And the question that I want to talk about, move towards, is where is this metric coming from and can we learn it? But before that, there was a question to start off.
Maybe you're going to address it?
Maybe. There's only one way to find out.
Do you want me to find out?
Yeah, go ahead.
Okay. So in regards to the metric used in individual fairness, like we know that this metric, individual fairness are similar individuals treated similarly. Do we have assumptions about the features in this metric? Like, do we make assumptions that excludes things that we typically consider group fairness, like sensitive attributes? Are these attributes that like accrue in some way to whatever task is happening?
Good question. So the question was about what do we assume, I guess, about the metric and about the features used by the metric. So for example, are sensitive features like race or sex, are we allowed to use that in the metric? So the answer is many layered, but let me give a couple of layers of the answer. So the first thing, where is this metric? What is this metric? That's super relevant for what I want to talk about in this hour. So I think of the metric as society's best effort for defining fairness for the task we have at hand. Perhaps with the features we have at hand, but I think society can also have an input on what the features are. So it's sort of in my imagination, and we'll talk about this in a moment, and maybe Cynthia can say what happens in her imagination. But in my imagination, there's sociologists and ethicists and lawyers and demographers and economists and computer scientists, and they all come and they sit at a giant round table and they discuss the metric. And they come up with the best features they can think of that should be used for a task. Say, I don't know, we're talking about insurance or we're talking about loans. So they all discuss and they come up with kind of the best effort, state-of-the-art metric for whom should be treated similarly to whom. And that's sort of canonized and used. And the nice thing is that this metric is out there. It's in the open. And in the paper, I think they call that sunshine for the metric. So if we understand, for example, that some feature we are using is a vector that is sort of inappropriately conveying bias, or there's a feature we're not using that we would like to include in the metric to have it sort of revised, we can do that, and we can revise the metric. So that's kind of the idealized.
Just remind about Kohler-Hausman.
About?
Kohler-Hausman, the Kohler-Hausman quote about you can't separate sex or...
Oh yeah, the reminder about the Kohler-Hausman quote that you can't separate sex from the other, or race from the other features. So I think what Cynthia's getting at is the second thing I wanted to emphasize in my answer, which is that actually it can be perfectly appropriate and necessary to use the sensitive features. Because if, for example, in our protected group, the qualified loan applicants somehow look different from the general population, it's very hard to get at that difference and have an appropriate metric without either explicitly or implicitly using the sensitive feature. So I actually think that carefully using the sensitive features is necessary, is important, and a frustrating legal fact is that in some settings it can be illegal in the United States to use the sensitive feature, even if you're doing it in a perfectly well-intentioned and, as far as we can tell, beneficial way for the protected groups. It might still be illegal. The last point I want to make is that ignoring the sensitive feature makes no sense at all to me, because the sensitive feature is, as Cynthia was saying, sort of holographically embedded in all the other features. So you could explicitly be ignoring race, but if you're using zip code, and we have redlining and zip code, there's a terrible history in terms of housing and zip codes, and it's very correlated with race. So I don't think that ignoring the sensitive attribute really makes a lot of sense, because it's being carried through all the other attributes and their connection, and the connections between them. Okay. Cynthia, do you have anything to add? This is generally about the metric.
What he said. But also, we're going to talk about this a lot on Wednesday.
Okay, Cynthia said we're going to talk a lot about this on Wednesday. After enthusiastically endorsing my answer, I should add. Okay. So, I do want to talk about, if I can get this mask thing together. Okay, I want to talk about, so we said that once we have the metric, we can define what it means to do machine learning, and we can have metric fair, individually fair machine learning, and it's perfectly natural to ask, and this is what we started getting at, where is this metric coming from? Okay, so one answer is, the kind of the round table where everyone is convened, and we're getting this sort of idealized world, and that's simply, the experts are telling us exactly what the metric is. But maybe, that's not always realistic, and maybe, the experts will do that for us when we're talking about, medical insurance, but they won't do it for us when we're talking about, shampoo ads. So where does the metric come from, and how much information do we know about the metric? So what I want to emphasize, when we talk about empirical risk minimization and doing fairness by basically finding the best fair classifier on the labeled examples we have at hand, we didn't really care about the value of the metric outside the sample that we had. What we wanted to see was the distances for the sample that we have at hand, or even just a matching on the sample that we have at hand. And once we verify that fairness holds there, it sort of automatically, we have these generalization theorems, uniform convergence, automatically fairness applied to the general population. So when we're talking about where does the metric come from, I don't have a great answer, and there's this idealized world, and there are several answers that I can give you, and I want to dwell on very nice work by Elvento that Cynthia mentioned about learning the metric or approximations of the metric. But first I want to notice that maybe we only need the distances between xi and xj for xi and xj in our training sample. Okay, that was certainly the case in the setting of fair pack learning, or pack-F learning. That's really all we used in terms of being able to see whether we satisfy fairness on our sample. There's another, so that's already good, right? Because maybe the panel of experts doesn't need to define the metric for any possible xi that we might encounter anywhere in the world, but they only need to debate the xi and xj we have in hand. And of course, the panel of experts is idealized. Maybe this is just the legal counsel of a tech company, or the responsible computing council in a tech company. So maybe they only need to do this for the training sample. Of course, the training sample could be large, so nonetheless, that's better than needing a fully specified metric. On the flip side, so that's better than needing the whole metric. Still, being able to quantify what the appropriate distance is between two individuals, given their features, that can be hard. So, I don't know, I'm not, just think about it. The data is multidimensional. We, come up with a number. Here, I'm showing you Alice and Bob. Tell me what the distance between them is for fairness. I don't know. It's a hard question to answer. Okay? So I want to talk about other approaches. One approach which I'll only mention is the Fairness Arbiter. So I want you to know about this stuff. So it's starting in work by Gimel et al. From 18, and also a more recent work of Bekavod et al. And what they imagine is that we just have this, we're coming up with our classifiers. They're in an online setting. I'll talk about online settings tomorrow. It doesn't really matter. I'm translating that. In case you look at the papers, I'm going to translate. Just know that the way I'm describing it is not exactly how it's described in the papers. So they imagine an iterative process where we propose our hypothesis, and we bring it to the arbiter. And the arbiter says, is it fair or not? So there's no explicit use of the metric. There is only this arbiter. And the arbiter is supposed to say, if there are a pair of individuals in our sample that are not being treated fairly, where there's a fairness violation, according to the current classifier, then the arbiter is supposed to scream, fairness violation, look, xi and xj, the difference between their classifications is too large. It doesn't need to tell us what their actual distance is. It's just telling us the distance is too large. You need to correct on these two. Okay? So what they show is that with such a fairness arbiter, you can quickly converge. So after not too many iterations, you can actually always learn a hypothesis that is fair with respect to the underlying metric and will also be competitive in terms of accuracy. Okay? So it's nice in the sense that there are no explicit distances being produced by the arbiter. This arbiter that we are imagining just needs to identify fairness violations. Now, of course, I think it's a really nice relaxation, but how is the arbiter doing this without actually coming up with distances, right? Like Alice and Bob, the difference between their classifications, statistical distance, is 0.2. Okay, so the arbiter now needs to decide, is the distance in the metric between them bigger than 0.2 or smaller than 0.2? So it's a relaxation. Somewhere in the belly of this arbiter, there is a metric, and if I go back to Cynthia's lecture, we have this conjecture, the metric conjecture, that says that in any system that is really, really promoting fairness, somewhere there's a metric in its belly. Okay, questions about that?
Is the arbiter always correct? Like, can he make mistakes?
In their works, I believe the arbiter always has to be correct. It's an interesting technical question. Yeah, I think you'd probably be able to get away, well, it depends on what kinds of mistakes you want to allow. So interesting technical question to think about. I think there are lots of questions, right? Like, okay, so we want to minimize our access to the metric or assume minimal knowledge or make the job of the arbiters or the experts easier. What kinds of models and abstractions can you guys come up with? I think it's an excellent research question. Yeah.
I assume the arbiter actually can't just like query a few mistakes and stuff here. In the sense that if the underlying metric is actually a contradiction and everything breaks down.
If the underlying metric is?
If the fairness arbiter was a human who was like, I feel like this is unfair, but didn't do so in a way that was fundamentally based on the metric, that like contradict itself.
Yeah, is it a follow-up to the previous question, if the arbiter is making mistakes? Yeah, I think you'd need to come up with some intelligent model. Like the arbiter isn't saying nonsense, but if it's making a mistake, with some bounded probability, and that, certainly if that's IID, then maybe you can do, well, I don't know. It's worth some thought.
Sorry for yet another technical question. Does the fairness arbiter
No, never apologize for technical questions.
have to satisfy the triangle inequality in a sense? That is, does its decisions, do they have to come from what's abstractly metric?
I think the answer is no. I don't think that they need to assume a triangle inequality, but I'm not sure. I don't think the triangle inequality comes up. So the earlier work of Gemmel et al. Assumed that the underlying metric had some structure. The more recent work, which is just from this year, does not assume the structure, the Mahalanobis structure on the metric, and I believe they don't need to assume the triangle inequality. By the way, neither did anything we did up until this point, other than, I think, Cynthia's differential privacy-based algorithm. Today we will use or right now we are going to use the triangle inequality. Okay, good. So what I want to talk about, what I want to focus on today is this recent work by Elvento from 2019, I believe, about how we can approximate the metric using a very small number of distance queries. So if you remember one thing from her work, I think the thing I would like you to remember is that you can reduce, you can't get away from distance queries. You can't have zero. You can't know nothing. You can't know, you can't assume zero access to the distances, but you can reduce it exponentially. So instead of needing to query all of the distances, you only need a logarithmic number of distances. And exponential improvements are fundamental, so that's what I want to talk about today. Okay, so any suggestions if we're going to access, this will be fun if it's interactive. If we're going to access the metric, but we're not actually going to be able to query about the distances between individuals. Like we're not going to try to ask, what is the distance between Alice and Bob? Kind of easier questions to ask.
Can you ask if Alice and Bob are further away, closer or further apart than Alice and Caroline?
Exactly. Okay, so that's a perfect suggestion, and that tends to be, or the belief is that that would be easier for humans to do. So, what was your name? Laura. So Laura's suggestion is, rather than trying to pinpoint the distance between Alice and Bob, just ask, is Alice or Bob closer to Carol? Okay, which of them is closer to Carol? That's what we call a triplet query. Right, is A or B closer to C? Okay, so qualitatively, that feels like an easier question to answer, right? You have some applicants, think about applicants for college or for graduate school. You have some reference point. You have Carol as your reference point, and now Alice and Bob come along, and you just need to determine which of them is closer. That seems like a qualitatively easier question for a human to answer than to actually spit out a number detailing the distance between Alice and Bob. And these are the kinds of queries I want to focus on, but some other queries you could, those are what we'll call triplet queries. You could think about a quad query where we have A, B, C, and D. And the question is the distance between A and B smaller or larger than the distance between C and D? And throughout, we can, I'm happy with approximate answers. So if the distance between A and B is really, really close to the distance between C and D, that doesn't really concern me. Answer whatever you want to answer. But if there's a significant difference, I want to know. So are A and B closer to each other than C and D? Carol and David. So good. So I think that's one really beautiful idea from Ilvento's work is to, and maybe it has its roots in earlier, I don't know, Cynthia, is there other research that has kind of talked about these things?
No.
Yeah. So one, beautiful idea is that we can have these kind of easier queries, and maybe there are other things, and this is a good also chance to involve social scientists, and if there are people with a social science background in the audience, kind of, are there things that are easier to measure than, really spitting out a complete distance between two people? So we're going to use these triplet queries. And the second beautiful idea is that once we have these triplet queries, we can sort of sort individuals according to their distance from some reference point, from some other individual. Okay, right, this is one idea. And second important idea is to use these triplet queries to sort, say, all the people in our training set, x1 to xm, by distance from R, a reference point. As Cynthia said, R is just some lucky victim, some individual that we pick. And the point is that once you sort x1 to xm, so we arrange them on the line, this is R, and maybe the closest point is x2, and then x5, and then x1. That already tells us something about the distances between them. And in particular, this can give us, we can use this to get, at the very least, approximations or estimates of the distances between the individuals. So I can approximate or estimate the distance between x2 and x5 to be the difference between x2's distance from R and x5's distance from R. And please suspend your disbelief. I told you that I wouldn't use distances, so we'll need to use a few of them. We'll talk about how we do that. But before we talk about how we do that using a few distance queries, the point is that if I compare these two, the distance of x5 from the reference point and x2 from the reference point, the difference between these, we'll see it. Using the triangle inequality gives me an underestimate of the distance between x2 and x5 according to the metric. Okay? So I can get, using triplet queries and a few distance queries, I can sort of sort everyone on the line from R to infinity. And then I can use this sorting to get an underestimate for the distances between individuals. And underestimates are useful. I mean, of course, the underestimate could be that the difference between everyone is 0, and then I've learned nothing, right? Okay, so I'm just going to enforce a super strong, overly strong fairness constraint, but hopefully not. Hopefully the underestimates are useful, and if I use them to formulate sort of approximate fairness constraints, maybe I'm being overly conservative, but I'm doing something. Okay, so using just a few distance queries, I have these underestimates of the distances between individuals, and I use these to achieve outcomes that are possibly even more fair than they need to be, hopefully not too much fair, and we'll talk about. Then I can use many different representatives and sort of refine my metric, but this is going to be the high-level plan. Okay, so the main point is we focus on using these triplet queries. We use them to sort the individuals according to their distance from a representative. And that allows us, using only a few distance queries, to actually have some approximate potential underestimate of the distances between all the individuals, and we can use that to enforce fairness. Okay, so that's our high-level plan. The point is getting there are many points. But one important point is that an underestimate is just fine. Okay, it's certainly a place to start from. Okay, if I'm fair with respect to an underestimate of the distances between individuals, I'm also fair with respect to the true distance. Okay, so really what I want to do, or what Elvento does, is construct an object that's called a submetric. Okay, so I'm going to call this d sub r. That's the submetric, or the new metric that we get by sorting people on the line and then taking the differences between their distances to r. And that's going to be what's called a gamma submetric. Gamma here is playing the same role as it did before. It's sort of like an additive approximation to the distance between individuals. So, okay, for a metric, remember, what were the properties we had? We had symmetry. We had that it's non-negative. And that's also true for a submetric. We had the triangle inequality for a metric. We don't need that for a submetric, so x. And we had, I don't really care about this indiscernibility property too much. For a metric, if the distance between x and x prime is 0, x has to be equal to x prime. You could have a pseudo-metric where that doesn't hold. Let's forget about that property. So the triangle inequality says the distance between any x and x prime, basically you can't shorten the distance between x and x prime by taking a shortcut through r or through any other r. Okay, so the sum of distances from x to r and r to x prime cannot be smaller than the distance from x to x prime. Okay, there's no triangle shortcuts. Okay, so for a submetric also, I'm not requiring for that to hold. What I am requiring for the submetric is that the distance, according to the submetric, is bounded by the true metric. So d sub r is a submetric of d. And that means that the distance, according to d sub r, is always at most the distance by d up to a gamma additive slack. Okay, that's a gamma submetric. Okay. And the idea is going to be to use, by sorting people on the line from R and then using a few distance queries, we're going to be able to get a gamma submetric of the true metric, and we'll use that for fairness. Okay, so just to maybe so, suppose we have our 3 points A, B, and C, and some distances, I don't know, 0.3, 0.2, 0.4. I hope nothing is violating the triangle inequality. So that's D. So you can obtain all sorts of submetrics, right? Like you can contract the distance here to be 0. Right, that's a submetric of D. Notice it doesn't satisfy the triangle inequality anymore, because you can get from A to C directly, the distance you pay is 0.4, but if you go through B, it's only 0.3, and that's fine. It's still a submetric. Or I don't know, we could add gamma here because we're allowed to have the distances grow by gamma. I hope it's clear. Okay, so that's the object that we want to learn. We want to learn a submetric of the original metric, and the claim is that if we are individually fair with respect to a submetric, we will also be individually fair with respect to the original metric. Okay. So if H is individually fair with respect to a gamma submetric, D prime, then H is also, according to our previous terminology, approximately individually fair up to this extra added gamma slack with respect to the original metric D. And the proof is by construction, right? If for every x and x prime, the difference between their distributions is at most the distance according to D prime, that's at most gamma more than the distance according to D, QED. Okay, so learning a submetric is a really good start because it lets us guarantee individual fairness, and hopefully it's easier than learning the entire metric. Okay, so now what I want to claim is that if we do sort, so I need to tell you how we sort. We use the triplet queries to sort the individuals on the line from R. But if we did it, I want to claim that we do have a submetric. Okay, so I'm going to define d sub r, the distance between x and x prime. That is the distance, according to the original metric, between x and r, the difference between the distances of x and x prime from R. Okay, so that's again, if I have my line, and here's R, and here's x, and here's x prime. So the distance between them according to the submetric is going to be this minus this. Sorry, this minus this, which is also known as kind of this interval on the line. Okay, oh, sorry, so I just defined it. So I claim this is a submetric of the original metric. Okay, so what do I need to show? Symmetry and non-negativity are by design. There's an absolute value here. So switching the roles of x and x prime doesn't change anything. And it's non-negative because there's an absolute value. Okay, so the only thing we need to show is that it's that it's always bounded from above by the true distance. Okay, and this is going to be a consequence of the triangle inequality. Yikes. Yeah, so by the triangle inequality, if I look at the distance between x and r, that's at most the distance between x and x prime plus the distance between x prime and r. Right, that's just the triangle inequality for D, for the original metric D. And then by switching things around, I get that the distance between x and x prime bounds from above. I'm just subtracting the distance between x prime and r from both sides. So it bounds from above the difference between the distance of x from r and the distance of x prime from r. And you could do the same thing by, you could flip the role. You could write here x prime, replace x with x prime here, and x with x prime, and flip x and x prime here, and you would get that also the reverse difference is bounded from above by the distance between x and x prime, and so the absolute value has to be bounded from above by the distance between x and x prime. Okay? So if we can sort the people on the line, and if then we can use that to get a good approximation to this distance, this submetric d sub r, these differences between their distances from r, then we will be in good shape for guaranteeing individual fairness. Maybe we're being too conservative, but certainly we will be guaranteeing individual fairness. Is that clear?
So in this case, it's gamma equals 0.
Say again?
In this case, it's gamma 0.
In this case, gamma equals 0, yes. Yeah, and what's going to happen actually when we sort them on the line, we're not going to be able to get our hands on exactly d sub r. We'll have a gamma approximation to it, and that'll give us a gamma submetric. Okay? To actually reconstruct d sub r, you do need to know all the pairwise all the distances from r. But once we settle for a gamma approximation, we'll be able to use many, many fewer distance queries. Okay. Good. So we have two goals now, or we have two steps that we need to make. The first is to show how to sort the xi's by their distance from R. And the second is how to use that sorted list in order to get a good approximation to the submetric, d sub r. So far, so good? Good. So sorting. So I'm imagining throughout, I'm staying in the setting we had before, where I imagine that I have some sample of individuals, x1 through xm, and I sort of want to get an approximation of the metric for that sample. But you could think about doing this for all the individuals in the universe. It doesn't have to be necessarily in this machine learning setting where you're sampling from an underlying distribution. I don't want to keep switching settings. So let's imagine still that we have our sample, x1 through xm, and we want to have an approximation of the metric for that sample. Okay? So sorting. So I want to do that. So I want to sort x1 through xm by distance from some reference point r, representative r. And I'll do it using order m log m triplet queries. Okay, so I am asking a linear number of queries, but they're triplet queries. They're not the distance queries that we were worried about before. Hopefully, these are easier. Okay, so and the algorithm that we want to use, we're sorting. So back to if you've taken an algorithms class, this should look familiar, but we'll remind ourselves. We'll just use merge sort. Sorry, nothing more sophisticated than that. I hope you're not too. If you're very disappointed, we can discuss more advanced sorting algorithms over the break later. So I take my individuals, x1 up to xm, that I want to sort, and I divide them into a left half, m over 2 people on the left, m over 2 people on the right, and now just recursively sort the left half and the right half, and then merge these sorted lists. Okay, so now L has been sorted, R has been sorted, and I just want to merge these sorted lists, and we can do that. So far, I should say what the stopping condition for the recursion is. Yeah, so if m equals 1, so if I just have one example, then I do nothing. Otherwise, divide into 2 halves, sort the left, sort the right, and then merge the sorted lists. And this can be done using size of L plus size of R triplet queries. Okay, so that's the algorithm. Yeah, we'll talk in a minute about merging sorted lists, just because it's fun, and some of us may not have seen it, or it's been a while since we've seen it. The point is that if you believe me that we can merge sorted lists using a linear number of queries, the size of the left plus the size of the right lists, then the complexity of this whole thing is going to be, of this whole algorithm is going to be m log m. Okay, so that's homework to convince yourself of it if you haven't seen. If you haven't seen that. Who has seen merge sort? Sorry, I'll ask your question before.
Yeah, before you go too far. So back to the case where you have this claim when gamma equals 0. So it seems like whenever I have a metric, I can define a new metric where I don't lose anything in terms of fairness. Right, you have 0, 0 individual fairness, but does that hurt your accuracy?
Yeah, so the question was, it seems like I'm cheating, right? I think that's basically what you're saying. You were polite about it, but you're asking if we're cheating because, I'm inventing out of thin air this kind of submetric by using very few distance queries, and I'm telling you that you're not losing anything in terms of fairness, so what gives? And as you were saying, what gives is what you would pay in terms of accuracy, or we might be being overly conservative here in terms of the distances. So we're enforcing we might be enforcing a much stronger fairness constraint than what we really need. And that would hurt accuracy or utility. Okay, show of hands. Who would like to go through the merging of the sorted lists? Okay, I have a definite no. I have a yes. And everyone else is shy. Okay, so since we have a yes, and since it'll be fun, let's do it. So it's the kind of thing where if I try to do it out of thin air, it won't work out. But okay, so suppose we have our x1 up to x6. Okay, and now we divide them into x1 up to x3 and x4 up to x5. And suppose that magically when we divide them and we sort each half, the left half comes out sorted in the same order, and the right, well, let's say the right half switches something. Okay, so now the left side is sorted and the right side is sorted, and my claim is that with a linear number of triplet queries, we can merge these two lists that are individually sorted into a globally sorted list. And the way we do that is we start with a pointer to the smallest item in each of the lists, and we compare. Okay, so now we ask who is closer, who has a smaller distance from R. Is it x1 or is it x5? Okay, because we want the smallest element in both of these lists to be our first element, and suppose it comes back and says x1, so we write x1, and we move our pointer ahead by 1 to x2. x5 stays in the same place. And now we want the second smallest item, so we just need to compare x2 and x5. Right? It's not, the second smallest item is not suddenly going to be x4, right? Because this list is sorted and this list is sorted. So we compare x2 and x5 with R, and suppose it comes back and says x2 is closer. So now we write down x2, and we advance the pointer. And we keep going. We compare x3 and x5, and now the answer comes out as x5, so we move this pointer ahead. We compare x4 and x3, maybe it's x4. And the point is that every time we're doing a comparison, it's one triplet query, and a pointer moves forward. Okay, so the number of triplet queries we're going to make is at most the number of elements in the two lists. Okay? So we do our last comparison. Maybe it's x3 and then x6, and we're done. Okay, questions? No questions. Good, so now we have our sorted list. Okay, so we have sorted all the elements according to their distances from R. So I don't know, yeah, we have x1 and x2, and then we have x5, x4. But we have no idea, remember, we need to actually approximate the difference between the distance of x2 from R and the distance of x1 from R. We don't know, we sort of have a qualitative ordering, but we don't know quantitatively what the distances are. So of course, we could ask m distance queries and figure out the distances and perfectly have the submetric d sub R. But then we've asked a linear number of distance queries. And the whole point, the whole exciting promise that I made in the beginning was that we can do this using a logarithmic number of distance queries. Okay? That's really the point of what we want to do. So any suggestions for how to do it? A random projection into Hilbert space. No, I can't. It's too sophisticated for me. So I don't know how I feel about a random projection, because it might be that, there's a couple of points, a very small number of points, where the distances become really large, like where the distances start growing. So I sort of really need, I do need to figure out what's going on this line. I don't know if something adaptive needs to happen. I'm not sure that a random projection would work. Okay, so the idea is to, the line is already a one-dimensional projection of a very sophisticated reality, you're right. But actually figuring out what's going on the line, I can't just probe random locations, I don't think. Yeah, I think that would be, it's not the algorithm, so it's not the algorithm that appeared in Elvento's paper, or the one I'm going to present, but I actually think something like that would work, kind of trying to find the median distance or something like that, and then recursing probably would work. It's not the algorithm I'm going to show, so yeah. Okay, so let's call this sort to dist. So I want using only a logarithmic number of distance queries to come up with an approximation of all of these individuals' distances from R. Okay, so my input is the sorted list. I'm renaming them so that they're sorted now, x1 through xm. And I want to output a gamma submetric, so an approximation to the submetric dr, let's call it dr prime, over these individuals x1 through xm. So I have my, it's going to be a recursive algorithm. So I get my list of individuals, and first I check what's the difference between the leftmost point and the rightmost point. If that difference is small, if it's just gamma, if all of these points are really at about the same distance from R, then I just collapse all of them together, and I say all of their distances from R are like the first point. Okay? So if we don't need an absolute value here, so the distance, and here I'm making a distance query, so you have to keep me honest and charge me for it. Okay? I can't do this too many times, but I am going to do a distance query, and I check that the distance between the rightmost point and the difference between the distance from R of the rightmost and leftmost point, if that's at most gamma, then I just collapse everyone, then I can halt. So that's nice for a recursive algorithm when we can halt. And I'm collapsing all of these points. For all of them, I'm saying that the distance from R is the distance of the leftmost point. Okay? And notice that if this is true, if the difference is at most gamma, then this will be a gamma approximation to the submetric. Okay? Okay, otherwise, what can I do? I'll just recurse. Okay, I'll chop this collection of individuals in half, and I'll recurse on the left half and recurse on the right half. So otherwise, I'll just recurse on x1 through xm over 2, still sorted, and on xm over 2 up to xm.
Sorry, I'm confused. I thought you wanted to recover the distances, the submetric distances between xi's and xj's.
Yeah, so I'm going to
You declare all these distances to be zeros?
Good. So let me rewrite this. So I'm going to pinpoint the position, you're right, of xi as the distance from between x1 and R. And then to do the pairwise distances, I'll just do the differences between these values. So let's just give it a different letter name to make that clearer. Maybe let's call it P for position. So I'm just collapsing the position of xi to the leftmost point, and then d sub r prime of xi and xj is the difference between these two positions. Okay, so somehow I'm placing these points on the line. And instead of, what ideally I would want is the position of each point to be exactly its distance from R. That's the submetric that I want. And now I'm doing an approximation to this position. Good. So the point is that the position that I'm computing for each point is within gamma of its correct distance from R, right? If the difference, if this whole, if my whole collection of points is within gamma of each other, then the position of any point is within gamma of the leftmost point.
So for one recursive, at the end of one recursive call, we're going to assign everything from this, at this halting point, everything gets the same position.
Yes.
So then, can you think of it as you're putting all these points in the same bucket?
Yeah, you sort of, I think of it as that you're just like collapsing all of them to the leftmost point.
And then the submetric on that bucket will be 0.
The submetric on that pocket, yeah, on all the collapse point will be 0, and between kind of different halting recursive calls, there will be some distance, which is the difference between the positions.
So at the end of the day, you always produce a function into R, which is Lipschitz, right? That's your...
Can you ask it again?
At the end of the day, you position all your points on R in a kind of Lipschitz way.
Do I position them in a Lipschitz way?
Right? Because you have a submetric condition that the new distance, the d prime distance, is always less than the original distance.
Yeah.
And the d prime distance is just the distance on R. So you produce the Lipschitz function into R. And you declare that to be the metric.
Yeah, I don't want to get, I'm not sure what you mean when you say that it's a Lipschitz function, so I don't.
With respect to your original metric, right? Because the new distances are less.
Good, yes, yes. So any points, yeah. Any points that were super close according to the original metric will remain super close. Points that were far away might collapse to be very close. And we'll talk about that.
You just produced a Lipschitz function and you claim that that is the metric.
And I use it as if it was the metric. Yes. Okay, so, oh, sorry, yeah.
If you still don't find distances within gamma and the second step, do you keep recursing? And if so, is that an exponential reduction? Because if you kept recursing, you'd have a total of 5 distance queries.
So you're asking about the accounting, and you should be asking about how many distance queries I'm making. So we'll analyze that. But kind of the point is that every time I'm doing, in every recursive call that I'm making, it begins with 2 distance queries. Okay, to the leftmost point and the rightmost point, and then we decide whether to halt or to recurse. And now the question is, how many recursive calls am I going to make? I gave away the game and I said it was going to be logarithmic in M, but I need to prove that. Okay, so it's not a trivial proof or anything like that. We need to argue it. Good questions. Okay, so kind of just in terms of correctness, I hope I've convinced you that what I produce here, this D sub R that I'm producing, is a gamma submetric of D. And now the question was being asked, and quite right, is, okay, but how many distance queries are we actually making? Are we saving some? Are we doing something non-trivial here? So my claim is that the number of distance queries in total is order of log m over gamma. Okay, and really what I want to do for this is examine, there's kind of like a tree of recursive calls. Right? We start with our parent for the recursion, and we have the dist. So what I want to keep track of are 2 things. I have m kind of individuals in the beginning. And I'll call this for any internal node in the recursion tree. I can talk about for an internal node u, how many individuals are in this recursion. And then also I can look at the distance. I call that delta u, which is the difference between the distance of the leftmost point and the rightmost point from R. Okay. And then we do a recursive call, and maybe in the first recursion, we split half the elements to the left, half the elements to the right. And now, there's a certain, we're sort of covering the interval of distances. If R is a distance 0 from R, and the farthest point is a distance, xm, which is kind of the sorted, is at some distance which is at most 1 from R, then we have some interval on the real line of the distances of the xi's that are involved in each recursive call. And maybe for this recursive call, the call to the right half just terminates. Now the distance between everyone is gamma, but this branch continues, and now maybe it terminates here. And we just have some tree of recursive calls. Is that clear? So basically what we're asking is how many nodes are in this tree, right? That's going to be, in every node we make 2 distance calls. So how many nodes, how large is the tree? So to do that, I want to talk about, there are 3, other than the leaves, so the leaves are sort of where we halt, there are 3 types of nodes, okay? So type 1 nodes are the ones where both recursions are leaves. So they terminate immediately. Okay, so how many nodes of this type can we have? Okay, so each node, when we begin, the difference between the distance of the leftmost point and the rightmost point from R is at least gamma, because we're not halting. We are recursing. But then both leaves are less than gamma, so we're not recursing on them. So we have here nodes, each of which is covering gamma on the line between R and xm. And they're all disjoint, right? There's no further recursion, so all of them are disjoint. Each of them covers gamma, so how many can there be? So they need to cover the interval between 0 and at most 1. Each of them covers a chunk of size at least gamma, so there are at most 1 over gamma of them. Right? Easy. Okay, type 2 nodes, where basically neither one of the recursions terminates immediately. Okay, so, that means that both of the children of this node are going to cover at least gamma interval, at least a gamma interval, because they're not halting. So this node covers at least 2 gamma itself. And how many nodes of this type can there be? So my claim is, again, that the number of type 2 nodes is about 1 over gamma. And I guess that's food for thought. How am I doing on time? I'm out of time. So the way to do it is through induction, or one way to see it is through induction. So let's look, so for a node U of type 2, where the distance of U, meaning the difference between its leftmost and rightmost point, is at least I times gamma. And we're going to do induction over I. So the claim is for every node of this type, whose distance is more than I times gamma, the number of type 2 nodes in its subtree the number of type 2 descendants is at most I. Sorry. If let's do it by induction over I, and let's say that all of the deltas are integer multiples of gamma. It doesn't really matter that they're integer multiples. So first, if a node is covering 2 gamma and is of type 2, then it has 2 children, each of which they're both not terminating immediately, so they both need to be more than gamma. So that's the base of the induction. And then once you have this induction in place, if you have a node that has weight I plus 1 times gamma, one of its children will have weight at least gamma, and the other one at most I times gamma, and you just inductively use your hypothesis. You just use your induction hypothesis and you're done. Okay, so this tells us, and I'm going a little fast because I'm out of time, so that's something to think about. I've sort of set it up for you. And now the slightly trickier ones are the type 3 nodes, where exactly one recursion terminates immediately. And up until now, we just had 1 over gamma nodes, so this is where we're going to pay log m over gamma. And the point is that if I look at a path, the main point to think about is, suppose I have some path where all the nodes are of type 1. Okay, so we just have one call. We have one call that terminates immediately. So like, for example, this path. We always have one call that terminates immediately. So how many nodes can there be on a path of type 3 nodes? So we're just on a path. All of them are type 3. How many of them can there be? Well, every time the number, one call is terminating immediately, and the other one, we have just half the elements. Right? We've cut the number of elements by half. So there could only be log m nodes of type 3 on any such path. And that's the key insight. Once you have that, you can show that there are at most 1 over alpha such paths, or there are at most order 1 over alpha nodes that are not on such a path, and at most 1 over alpha such paths. So any path of type 3 nodes has length at most log n. Okay, that's the key insight, and you can fill in the blanks. That's homework. So good. Putting it together, we have our algorithm. We sorted the individuals using merge sort, and then we assign distances using this sort-to-dist algorithm. And intuitively, every time we're making a recursive call, we're either sort of chopping off a gamma fraction of the segment, or we're cutting the number of individuals by half. That's a very loose intuition. So the total number, but we do get in the end that the total number of recursive calls is log m over gamma. Okay. So very briefly, we said it several times, but I want to emphasize it again. We're getting here an underestimate, a potential underestimate to the metric. So looking at it pictorially, maybe we're in two-dimensional space, and we picked our representative R here. And now we have x1 here. This is the true distance between R and x1. And we have x2 here. So there's some distance between x1 and x2. But they are both at the same distance from R. So this algorithm would collapse them together, right? We're just looking at distance from R. Essentially, we're drawing this line through R, and we're projecting. It's not exactly what we're doing, but at least morally, we're projecting the nodes onto this line. So we're collapsing these nodes. Even though they were far apart and there was some distance between them, our submetric is going to say the distance is 0. And what do we care? I mean, we still get fairness, right? We've just underestimated the distance. But exactly as was said here, that's going to hurt our accuracy. We're being too conservative. Okay? So one idea from Elvento's original paper, or one insight, is that, well, we could do this. This was a lot of fun. We can do it again. Right? We can pick another representative. Maybe we pick another representative, R2 here, and we do the same thing. And maybe we pick a third representative that's closer to sort of distinguishing these 2 points. So if we pick R3, Now the distance from R3 is really going to be a good approximation to the distance between x1 and x2. So we can pick different representatives, different representative points to try to cover the space. And then how would we merge all of the submetrics that we have? Take the soup, yeah, take the max, right? So we construct our different submetrics, and then for any pair, we look at the max distance given by any submetric. We use that. We know that any submetric distance we use will underestimate the true distance, so we still have individual fairness. And hopefully now, if we pick our representatives well, we can really get a nice, meaningful approximation to the metric. Yeah, so this gives us a way, in our setting of pack learning, we can just do this within the sample. We can also do it in other settings where we don't necessarily, maybe we're considering all the individuals in the universe. But it gives us a good way to meaningfully approximate the metric. And the amazing, the miracle is that we do this just using a logarithmic number of distance queries. And I think there's a lot more potentially to be discovered. One question that occurred to me as I was writing the notes is log m a lower bound? In what sense is it a lower bound, right? We could just output 0 for all the distances, so there is no lower bound. But is there something, my intuition is that there's something really meaningful happening here, and we couldn't accomplish it using less. Trying to formalize that would be nice. Yeah, I'll just say this is giving us distances within the sample. It's not telling us how to learn a metric that applies outside the sample. In the paper, there's some assumption about learning thresholds over these submetric distances that would allow you to really learn an approximation to the metric that generalizes out of sample. I think that's interesting, but then if you want to generalize out of sample, you have to make some assumption about the metric. The nice thing here is, for example, if we're doing fair pack learning, we don't need to know what the metric is outside the sample. We can just run this inside the sample. We get our underestimates for the metric, and we find the best fair classifier with respect to these distances, and we're done. OK, so I'm going to end here. I think tomorrow, Cynthia will talk more about composition and more fun stuff. And we will also move beyond individual fairness and talk about fairness when we don't have a metric. Great. So we're over time, but if you guys are really good at asking questions at the end when we force you to. So any questions?